Thank you for the invitation. So I want to talk about this title. So So I think you probably have heard about birational superrigidity in Agudo's talk, but let me still remind you what that is briefly. So so throughout this talk, I'm going to work over the complex numbers, and let me fix the notation. So X is always going to be Fano variety over this field of complex numbers. And so I say X is birationally superrigid. Maybe birationally rigid first. If for any birational map from X to the total space of a Murray fiber space, so this is a Murray fiber space, we have an isomorphism between these two objects. But in general, this isomorphism is not necessarily induced by this birational map. Okay? On the other hand, we say it is birationally superrigid if this isomorphism is indeed induced by this birational map. Okay, so that's the definition. And let me give you some examples and non-examples. So maybe first a non-example. So let's say I have a hypersurface in projective space. So this is a hypersurface of degree d in the projective space of dimension n+1. So throughout my talk, n is always going to be the dimension of X. Okay. So let's say this degree is at most n, so that the hypersurface has Fano index at least 2. So in this case, a general hyperplane section of X is still a Fano variety. So you can just take a pencil of these hyperplane sections to decompose X into a Fano vibration. So from our definition, this is not birationally rigid. So this has general fiber is Fano. So this is not birationally rigid. Okay. On the other hand, if you have index 1 hypersurface, so this is rather theorem. So if X is a hypersurface of degree n+1, smooth hypersurface, then it is birationally superrigid. Okay, and this is a theorem of a combination of many people's work, including Iskowski and Manning. In the case of quartic threefold, Shelsov up to dimension 7, and then Devaney and Mustasa. Up to dimension 11, I think, and then the general case is proved by Devaney. Okay. So here this is for every surface. So if okay. I see. I think I should always put Progekov's name before in here. Yeah. So as a remark, so the motivation for studying birational superrigidity and rigidity is to prove non-rationality of Fano varieties. So in particular, this theorem tells you that this hypersurface are not rational. So, okay. So I also want to give you some birationally rigid but not super rigid example. So, so if you allow some singularity for this hypersurface, so again, let's take X to be a degree n plus 1 hypersurface and Pn plus 1. But this time, with a singularity, an ordinary singularity. So ordinary means that the projective tangent cone is smooth of multiplicity n minus 1. Then, okay, so let me write the names first before I move this block. So this is proved by Meller for quadratic 3 folds, and then Puklikov in the general case. So for this kind of hypersurface, let's say this singular point is X. Then you can use the linear projection from this point to construct a birational involution of this hypersurface. So that's not hard to see. Then projection from X. Gives you a birational double cover of the projective space. So it induces a birational involution of X itself. So from the definition, you see that this is not birationally super rigid. On the other hand, so birationally super rigid. On the other hand, if under these conditions, the coefficients are general for this hypersurface, but if fx is general, under the above assumptions, then X is indeed birationally rigid. Okay? And furthermore, the birational automorphism group is exactly generated by this involution. Okay, so that's it. Yeah. So the main theorem is about this part. For generic. Yeah. Okay. So from these examples, as you can see from these examples, so birational rigidity and superrigidity, they are somewhat special properties of final varieties. So in general, the expectation is that which I'm not going to make sense, and it's hard to make sense here, that if you look at final index 1 final varieties, maybe mild singular. So they are usually birational rigid or super rigid. Okay. So that's the general philosophy. So in this talk, I want to investigate the following question for this kind of final, this kind of varieties. Namely, we'd like to know, is there a nice moduli space for this kind of special final varieties? Okay. So this is partly motivated by another two conjectures. So in general, we know that if you just consider the moduli space, moduli stack of final varieties, then it's going to be very bad. It's not even Hausdorff, so separated. So you need to put some conditions. So one of these conditions is given by K stability. So there is this Fock law K moduli conjecture that predicts that if you consider the moduli stack of K semi-stable Fano varieties with a fixed dimension and anti-canonical volume, then this is represented by an Artin stack of finite type. With a separated good moduli space. I should say N proper. Okay, so but what does this has to do with our question? So there is another conjectural picture by so it is conjectured by Kim, Okada, and Wang. Oh, sorry. Forgot the last word. Thank you. Yeah. So it's conjectured by this group of people that so if you have something that is birationally rigid, if you have a Fano variety that's birationally rigid, then they are actually K-stable. So I think some partial progress of this was made earlier by Odaka and Okada, and then they tracked this conjecture for many Fano threefolds that you might have heard in Takuto's talk. And also another partial progress was proved by Charlie and myself. So we show that instead of birationally rigid, we show that if X is birationally superrigid and the alpha invariant is at least 1/2, then the variety is K-stable. Okay, so it seems that this is can be expected in many cases. So if you combine these two pictures, it seems reasonable to ask a more precise version of the above question, namely, is the moduli functor of birational rigid Fano varieties or the moduli functor of birationally superrigid Fano varieties in a given dimension represented by a separated Riemann stack. Okay, so I'll explain why we have this refinement shortly. Okay, so yes.
If no birational rigidity and alpha needs to be bigger in order to make K stability?
Okay, can you say again? Sorry.
So if no birational rigidity, additional alpha in order to get K stable.
You mean only this alpha condition? So, so I think as you might have, yes. So it depends on whether you want to put smoothness. So yesterday in Yuchen's talk, he talked about this example of codimension 2 complete intersections with alpha equals to n-1/n, which is K unstable. So this is usually greater than 1/2, but this is singular with only one singular point. Yeah. So in general, this is false, but if you only allow smooth varieties, then I don't know the answer. Okay. Yeah. So the equality case is okay. Yeah. It's not in the introduction. Yeah, but in the actual content, we have that version. Okay. So the question over there on the right board, so you can basically decompose it into several parts. So you might have noticed that I don't put the volume assumption. So basically, you always have boundedness in a given dimension. So that's the first part you might want to ask. So the reason is that, so from the definition, actually birational rigidity or superrigidity will imply that the variety has terminal singularity. So it's going to be terminal Q factorial and p count number 1. But once you have a terminal singularity, then the result of Berkau on the BAB conjecture will tells you that in any given dimension, birational superrigid or rigid varieties, they form a bounded family. Okay. So at least boundedness is okay. So you may also notice that I replaced Artin stack by the Lim-Mumford stack. So the reason is that for any birational rigid or superrigid varieties, the automorphism group is always finite. Okay? And this is also very easy to see. So basically, if you have some group like GM or GA acting on the variety X, then you can take an open set of X such that the geometric quotient exists, but the fibers are one-dimensional. So this gives you basically a final vibration on your variety. So, but this is not allowed from the definition that I already raised for superrigidity and rigidity. So this will imply that X is not birationally rigid. Okay? So any birational rigid variety is going to have finite automorphism. Okay? Okay, so X is final, so you can embed this by this anti-canonical linear system, and then GI acts on this pluri-anti-canonical system. You can find an invariant hyperplane section, you cut it out, so you're left with an affine thing. And then on this affine varieties with a GI action, I don't remember what's the proof of this, but I think even for this group acting on a affine variety, you can take a affine subset on which the quotient exists. I can give you the reference data. I don't have it on top of my head. Yeah, but I think this is quite standard result. Yeah. Anyway, okay. So these two are the easy parts. So maybe the third thing you might wonder is about the separatedness of this moduli, if that even exists. So we don't know the answer for rigidity, but for superrigidity, this is okay. So together with Charlie, we basically show an evaluative criterion for this separatedness. So basically, if you have two families of flat families of final varieties over a curve, and so you have a point on this curve, and you assume that these two families, they are isomorphic away from the central fiber. So this is over the punctured curve. And both central fibers are birationally superrigid. Then the conclusion is that these two families, so this isomorphism X actually extends to an isomorphism of the total space over the curve. Okay, so this basically tells you that the modular space of this birational superrigid fund of varieties, if that module ever exists, it's going to be separated. So now we have a bounded family of fundamental varieties that parameterize this birational rigid of superrigid fundamental varieties. Oh, this one? It's like the proof like you have for this when you have two families where the alpha invariant of the central fiber add up to at least 1, then the two families are the same. It's quite similar. Yeah. But for birational rigid, we don't have this kind of description. So that's why it fails. At least we don't know how to prove it for rigid. Okay, so now even though we have this bounded family, it's not clear why, if you just look at the birational rigid or superrigid fibers, there are only finitely many locus for this. So a priori, there could be infinitely many fibers. So there could be a dense subset of fibers that are birationally superrigid, but the generic fiber or the very general fiber is not. Okay, so basically, you want to know that whether the locus of the fibers, where the fibers are birationally superrigid or rigid, is a constructible subset. Constructibility. So again, we don't know the answer for rigidity. But for superrigidity, this is a theorem of Shawcroft and Choi. So they show that if you have a flat family of fundamental varieties, then the set of fibers, the set of the base where the fibers are birationally superrigid is a constructible subset of the base. Okay. So basically, the idea is that so earlier I said if you have something that's birationally superrigid, it has to have this terminal Q factorial singularity of picon number 1. So take this locus up, which is constructible. On the other hand, if X satisfies this condition, but it's not superrigid, then what Shawcroft and Choi prove is that then they show that if it's not birationally superrigid, then there exists a terminal weak funnel variety of picon number 2 such that your original variety X can be obtained by running a minus KMMP, and you end up with X. Okay, so so because terminal weak final varieties from a bounded set by result of Berka, so. And so, and using this set, when you run the KMMP in this family, you end up with a constructible set of birational super-rigid guys, non-rigid guys, non-super-rigid guys. So the complement is also constructible. Okay, so that's the rough idea. So we are pretty close. So the remaining question. So if you are just looking for a family of final varieties that exactly parameterize all the super-rigid varieties where you allow repetitions, then this is what you have already. Okay? But if you want to have a moduli, you want to impose stronger conditions. So, so maybe naive guess is that so maybe this birational rigidity or super-rigidity, so maybe they are open conditions. So if you have a family, a flat family of final varieties, you want to know whether the set that I wrote down above is not just constructible, but actually an open subset of the base. So unfortunately, the answer for this question is no, at least in dimension 3. There are 2 examples that I can tell you. So for birational rigidity, this counterexample is given by Chelsov and Grinenko. So basically, so they consider quartic threefold, singular quartic threefold of the following form: FH equals. So these equations are homogeneous of degree 1, 3, 2, 2. And these 2 quadratic terms, they are not equal. Okay? So this gives you a singular quartic threefold that has a non-Q factorial singularity. But there exist 2 unprojections. So just think about this as a determinantal variety. So you can introduce an extra variable and get a birational map like this. So H equals Q2 of T. So this is a complete intersection with a singular point. And if you change the row of Q1 and Q2, you get the other one. So in general, so you get these 2 complete intersections, they are birational. But in general, for general choice of Q1 and Q2, they are not isomorphic. So this is not birational rigid. On the other hand, for some particular choice of Q1 and Q2, these 2 objects, they are isomorphic. So for those particular choice of the quadratic hypersurface, you get birational rigid complete intersections. So in other words, inside this families of complete intersections of quadratic and cubic, you have some special members that are birational rigid, but when you deform the equation, they become non-rigid. Oh, is there a question?
You can start like this complete intersection of quadratic and cubic with putting the double point. And just project from the double point. And then you get the square. And then you have so like midpoint of that discipline. So you don't have the slope, and you have another model of X2, which is also complete intersection of quadratic and cubic in B5. Also with the double point. But a priori they are not isomorphic. But sometimes they can. If they are not, basically we prove that this is non-isomorphic, by definition, they're not rigid because there's exactly two models. But if they are isomorphic, it becomes birational rigid. So it becomes birational.
What's your original question?
I think the question was, is it smooth? X1, X2 is smooth? No, it's
Oh, no, it's not. No.
ordinary double cube.
Yeah.
Smooth examples? No.
Yeah, we don't know smooth examples. Yeah. Even examples I'm going to present at the end is not smooth. Okay, so that's a counterexample for rigid ones in dimension 3. For super rigid ones, there is also an example by Chelsov and Park. So in this example, you consider a weighted hypersurface of degree 5 in this weighted projective space. Okay. So if I use the letter y for the last weighted homogeneous coordinate, you can write down the equation in the following form. So y squared term, linear term, and a constant term, where this f, g, and h, they are homogeneous in the first 4 variable. Okay? So this has degree 2 in the last variable. So that gives you a birational involution on the variety just by assigning, just by solving this quadratic equation. Okay, so this gives you a birational involution on the variety. Yeah, and in general, this is birational, so it's not an isomorphism of the variety. But if f divides g, then this gives you a biregular map. Okay? So what I actually show is that in this case, the variety X is birational superrigid, while in this case it's just birational rigid. Okay? So again, you have some smaller locus where the variety is birational superrigid. When you deform it, you get some non-trivial birational involution. Okay? So this tells you that superrigidity is not an open condition. Okay?
Maybe it's a failure smooth variety could be open.
Sorry?
Is it expected that it is?
No. This is a similar example like this, I guess, can be constructed for smooth varieties, probably too. I'm not sure, but I think this kind of, when birational involution can collapse to biregular. I think this is probably possible to do with smooth one, but I'm not sure. Examples are not known.
So-
Non-closed field cubic surface in P3, it's easy to hook up or non-closed. But this example actually just reminds me, it was discussed in details on Monday by Takuza Akara.
Yeah, okay. Okay, so that's already some bad news. On the other hand, if you are just interested in this modular question, openness is not what you really need. So the real question that you want to ask is whether birational rigidity or superrigidity is a locally closed property. Right? So unfortunately, the answer for this is also negative, and that's what I want to present in this talk. So the main theorem is that the answer is no for birational superrigidity. Okay, but again, I don't know the answer for rigidity. So what's the main construction? So basically, if you remember the earlier example I gave you about hypersurface with a very bad singularity that's birational rigid. So let me just recall that this result that if you have a hypersurface of degree n plus 1 with a point of multiplicity n minus 1, then this is birational rigid, but not birational superrigid, because there are birational involutions. Okay? So the idea is to start with this kind of example, and you degenerate it to a double cover of hypersurface. Okay? So here is the main construction. So let me just write down the explicit equation for degenerating a hypersurface into a double cover. Okay, so introduce an extra coordinate y. Okay, so let's say I have. Okay, so let me write down the equation and explain what they mean. Okay. So I'm going to do this inside a weighted projective space of dimension n plus 2. Okay. And this is a family of weighted complete intersections over the affine line with coordinate given by t. So when t is not 0, you can just solve y from this equation. And I want to assume that the degree of f is twice the degree of g also. So let's say this is m. So this is 2m, and degree of g is m. So these are just homogeneous coordinates in the first n plus 2 variables. So as you can see from the equations, when t is not 0, then you can eliminate y from the second equation. So it's basically a hypersurface given by this form, and this sits inside Pn plus 1. So this is a hypersurface of degree 2n. Okay. So we want to construct something that's birational superrigid. So it's better to have this hypersurface as a final index 1. So let's say this is just n plus 1. Okay. And on the other hand, if t is 0, then the central fiber is given by this form. So this is a double cover of the hypersurface given by the vanishing of G with a branch locus that's given by the intersection of the vanishing of F. Okay, so this is a one-dimensional family, and it's hard to expect that for a one-dimensional family you get counterexample to local closeness. So we need to put some parameter for these equations. So basically, what I want is that so inside this two-dimensional family, the general fibers, they are just index 1 smooth hypersurface. So those are birational superrigid. And there is a line of double covers. And there is also another line of singular objects. Okay? So along this line of singular objects, so maybe I picture this A2. So you have a line of double covers. and this is a line of singular objects. Okay, and you are degenerating singular hypersurface into a very singular double cover. So over the smooth locus, so these are birational superrigid because they are just smooth hypersurface of index 1. But for this singular hypersurface, they are not birational superrigid because of this reason. Okay? So what I want to claim is that along this double cover, they are all birational superrigid. So what this implies is that the locus of found varieties in this family that are birational superrigid is exactly the union of the origin and the part where this vertical line is removed. Okay? So at least the region is not locally closed.
Double covers separation region.
Sorry?
Can you repeat about the double covers? So this
This horizontal one? Let me write down the claim. So the main claim is the following. So maybe a theorem. So with this above family, so I assume that so the fibers I'll call X as T. So assume that this is smooth when the parameter S is not 0, and smooth away from a single point X, where X is just that multiplicity and minus 1 point. Okay, maybe I don't write this. When S is 0. Okay. That's one thing. So in general, we need some generality condition, but that's not too bad. So I need to assume that basically those singular objects, they are just singular at that particular point. Okay, so I assume that this F0, where F is the vanishing locus of this hypersurface. So they have ordinary singular point of multiplicity. Let me just write the following. So I think what I really want to say is that these central fibers, X, 0T, has smooth projective tangent cone, ordinary singularity at this singular point X. And multiplicity of this at the point X is just n minus 1. Okay. So then the claim is that so these are just some generality conditions that I need to assume for this construction to work. So the claim is that these fibers, they are birational superrigid if and only if you are at the origin or away from let me see, away from the line of double covers. Okay, is this clear? Okay. Okay, so so actually the actual content of this claim is the part that so the double covers, they are all birational superrigid, because as I said earlier, the smooth hypersurface, they are all birational superrigid by the results of many people, and this singular hypersurface with a point of this multiplicity, they are not birational superrigid. So S is 0 represent the singular objects.
They are not birational.
Yeah, but they are usually not birational superrigid. So, and T equals 0, yes, S not equal to 0. Yeah, thank you. Let me just remark that this is just some generality condition. So this is the double covers. S is the singular finals. Okay. Yeah, so I think I just confused myself. Yeah, so in this generality condition, let me just specify. So for the smooth hypersurface, for the singular hypersurface, it's not a big deal because they are never birational superrigid. What you really want is the singular central fiber at the origin is birational superrigid. Yeah, so for that I really mean this F0 and G0, they have ordinary singularity at X, and so is their complete intersection. So this means their projective tangent cone is smooth. Okay. Yeah. So the actual claim is about this this double covers. So what we really want to show is that these double covers, they are birational superrigid. So there is two parts. You have these smooth members, but you also have the very singular central members. So F0 is this hypersurface. So you are taking a double cover of hypersurface along a branch locus. But these two, they are usually so they are singular with a prescribed multiplicity. So I think this is 2n minus 1, which is 2n minus 2, and I think n minus 1. So so these two, they are usually singular at that point. And I require that when you take this double cover, the singularity, they are not too bad, because otherwise I have no guarantee about the superrigidity of the central singular fibers. Okay. So what I require is that you specify multiplicities so that this hypersurface, it has a multiplicity of the correct number. Yeah. And then you also want that the tangent cones are smooth, so that the singular central fiber is controlled.
What is n? I mean, n is bigger or equal than.
So n is n is always sufficiently large. Yeah. Okay. Let me change it. Okay. So let me separate the statement about birational superrigidity into two parts. So the first part is about smooth members of this family. So let's say I have so this is slightly more general. So let's just look at, so you can think about double covers as weighted complete intersections. So if I start with the weighted complete intersections inside some weighted projective space, where you have a bunch of weight 1 coordinates and a bunch of other coordinates. And let's say I fix this number of greater than 1 weights, so fix S, and R. So R is going to be the codimension of this complete intersection. So this is codimension R smooth. So it's not only quasi smooth, but actually smooth. Weighted complete intersections of final index 1. And meaning that the Picard group is generated by the anti-canonical. And you assume that this anti-canonical linear system is space point free. Then for these fixed numbers, there exists a sufficiently large integer n such that if the dimension of x is greater than this number, then these weighted complete intersections, they are always birationally superrigid. And actually, if you still remember one of the criterion that about this k-stability part, then you can actually also show that the alpha invariant is at least 1/2. So actually, they are also k-stable. Okay, so that's the statement for those smooth double covers. As for the singular guys, I don't want to just state it for that particular singular variety, because the technique can be actually applied to many other like singular final varieties. So this is partly joined with Yu Chen, who's in the audience. So you can actually apply this thing to singular hypersurface. So let's say X is a degree n+1 hypersurface inside Pn+1. And this has only ordinary singularity. So isolated ordinary singularity. And let's say the dimension is sufficiently large. Something like this is enough. Then the conclusion is that so let's say the multiplicity is at most n. Then, as you saw before, that with multiplicity n-1 is never birational superrigid. But what we can show is that if the multiplicity is at most n-2, so smaller than that, then this is birational superrigid. And if the multiplicity is at most n-1, then this is only birational rigid. And in this case, the birational automorphism group is generated by the automorphism group together with all the birational involutions that you get from projecting from a multiplicity n-1 point. And so the projective tangent cone is smooth. So this is just a hypersurface. Okay. So plot that singular point, you get a smooth exceptional divisor, and that also resolves the singularity. Okay. So again, I'm not going to go into detail for this part, but again, using some refined criterion for k-stability related to this superrigidity things, you can also show that when the multiplicity is at most n, which is the dimension, then the variety, this singular variety is k-stable. Okay, but I'm not going to details for this. Okay. So I only have a few minutes, so probably I'll skip the proof. But let me say a few words about some more questions. So as you see from this construction, birational superrigidity might not be the correct notion to consider if you are looking for a moduli. So maybe you want to ask what's the correct modification of this from the point of view of, yes. So, I mean, if you're just looking for a family that parameterize, so basically, for instance, yeah, I agree that for many construction it's fine. But if you want to have a representability, then so let's say, for instance, in this example, so you have this total space. So if you want to construct the modular, it's better to separate this point from the rest of this data. Yeah, yeah, but then you also have this line of double covers. So this is a family of super rigid Fano varieties. So you want to have this line mapping to your moduli space. But in that case, you don't have representability.
For the construction of, say, modular stable varieties,
Mm-hmm.
the first step is to establish that it's constructible.
Yeah.
So
Yeah.
you proceed from there.
So So you can have a family that parameterize up all the objects you want, but so what I say here is just a subtle issue about representability. Yeah. Yeah, but I agree with what you said earlier, that constructability is enough for many questions.
But then you don't have a path.
Discuss during the break.
Yeah, sure. We can discuss later. Yeah. Yeah. Let me just finish with this question. So so if you really want some local closeness, so let me say so let me give you a slightly different definition. So I think this is introduced by Ahmad Nizat and Okada. So so I say that X is birationally solid. If in the definition of birational rigidity and superrigidity, you only say that, so if you have a birational to a Mori fiber space with positive dimensional base, it's an isomorphism. So in other words, it can be birational to another Fano variety, but it cannot be birational to a Fano vibration. Okay? So essentially, you can think of this as like a more refined building blocks for Fano varieties. So my question is, so maybe this is
Better say such map will not exist.
So what's an example?
Yeah.
Do not exist.
Yeah. Thank you for your suggestion. Yeah. So for example, in the earlier example of Chelsov and Grinenko, you have this Fano variety that is birational to another non-isomorphic Fano variety, but that's the only Mori fiber space structure you can have. So they are not birational. Yeah, and of course you have something that's birational, super rigid or rigid, then it's this kind of, yeah. So so my question is, so I don't know. So far, in all the examples we construct, basically all the fibers are birational solid. So my personal feeling is that this might be the correct objects to consider if we are looking to parameterize Fano varieties from the birational geometry point of view. So maybe just put it as a very vague question. Again, is there a separated Deligne-Mumford stack for birationally solid Fano varieties? Okay. I think I'm out of time, so maybe I stop here. Thank you. I think that's still a conjecture. So I think in K-stability, it's actually conjecture that semi-stability is an open condition. And I think it's currently known by the work of Yuchen and Harrow that no, it's still a conjecture. Uniform K-stability is an open condition by the joint work of Yuchen and Harrow. And also smoothable case is known. In the smoothable cases, open property is known. But the singular case, we don't know. I don't know, actually. So we only know this for birational superrigid funnels. But I expect this might be true.
I have some comment.
Yes.
So if you take your example,
Yes.
this one basic, but if you assume n is 3,
Mm-hmm.
yeah, and you forget about this vertical
So
then for you get birational superrigid for if you just erase this vertical line,
mm-hmm.
you have only quartic hypersurface,
Mm-hmm.
smooth one,
Yes.
which is superrigid.
Yes.
And then the generation is a double cover of quartic,
Yes.
but it's not rigid, it's superrigid. It's so in some sense it's three-dimensional. It's partially understood this is three-dimensional case.
Mm-hmm. Mm-hmm.
Yeah. And
So I think So I think in dimension 3, basically, so this smooth families.
forget about singular length, the simplicity. Not
Yeah.
singular length.
Uh-huh.
You have this area
Yeah.
and this is the birational superrigid.
Yes.
But then this double cover.
Yes.
They rigid, but they're not birational superrigid because they have actually huge group of birational.
Yeah. Exactly.
So it's something it's like also three-dimensional.
So yeah, no, but I think if you remove this, so basically you are saying that in the in the dimensional 3 case, basically these smooth members, they are this smooth hypersurface, quartic smooth hypersurface, they are birational superrigid, and then these 2 vertical lines, they are not birational superrigid. Yeah, so I think that's your comment. Yeah. So that's why we need to increase the dimension and yeah.
What about properness of these variants?
No, I think they are in general not proper. So.
Do you have an example?
I mean, like even for this quartic 3-folds, I don't know how to compactify them using the superrigid guys. Because for quartic 3-folds, whenever you have a double point, it's not superrigid, and if you degenerate it to double covers, it's not superrigid either. So you are missing a lot of things on the boundary still.
So if you do that birational superrigidity like case stability, then this would be a counterexample?
You mean a counterexample for
Properness?
properties? I mean, if it only implies K-stability, I don't think that gives you counterexample for properties, because even for K-modular, I need to add in the semi-stable guys. And I don't know what semi-stable correspond to in the superrigid or rigid case. So I think that's the missing part.
Any other questions? If not,